Start there. What's the first thing you do?
Convert it to K?
Not even a Chem 2 thing. First thing you should always do is make sure you're writing the right chemical equation. Okay?
Yeah.
Write the chemical equation. Usually next thing is find moles or concentration if you need concentration, molarity, one of those two, whatever it is. So what is hypochlorous acid?
HClO.
HClO. Okay, so we have HClO, and what's it going to react with? Water. Okay, and what are we going to get?
H3.
H3O plus.
And ClO minus.
ClO minus. Okay. Just to kind of divert here for a second, what's our conjugate base? What's our conjugate base?
ClO minus.
ClO minus, because that's the thing that's going to gain a hydrogen in the products.
Yeah.
Right? Okay. All right. So now we need to set up an ice table. Right?
So we want to convert to K.
I guess we could write the equilibrium expression first. Doesn't matter. Either way, gotta do them both. So Ka is, what is Ka? H3O plus times ClO minus over, what goes on the bottom? HClO. Do I put the water down here?
It's liquid.
Why not?
It's liquid.
It's a liquid, right. Okay. What does square brackets mean? Square brackets means concentration in what units? Molarity. Molarity. But I don't have this in molarity, it's in percent composition. So I gotta turn that into molarity. Okay. So let's do a little review. What does 5% weight to volume mean? 5 grams of HClO4 per what? 100 mils of solution.
Yeah.
That's what weight to volume means, right? So we have 5 grams per 100 mils. Can we turn that into moles per liter?
Sure.
Okay. Yeah, if you want tears shed by your K1 teachers. Oh, let's see. So 5 grams per 100 mils is going to be equal to 50 grams per 1,000 mils. 52 and a half. Does that sound right?
Sounds about right.
52 and a half?
Yeah.
Okay, so 1 mole is 52 and a half grams. So just a little, yes?
What did you get 50 grams of?
Well, because 5% weight to volume means 5 grams per 100 mils. So right, multiply it by 10 over 10 to give me 1,000 mils, which is a liter. Right? But if I multiply the bottom by a 10, I gotta multiply the top by 10.
Yep.
Just algebra, right? So this is what, like 95%? 0.95?
Yeah, 0.95.
0.95? Okay. Okay. So we've turned percent weight to volume into molarity. Kind of a non sequitur, but the reason I gave you that is because that's the concentration, that's bleach. And that's actually the concentration of bleach, it's 5%. Okay, so, where do we go from here? Can you figure it out now? So what's 0.95? At the start. Okay, so that's, remember the ICE table? I is the initiative line, initial line, consume line, the equilibrium line. Okay, you guys get that?
Yeah.
So that means this is x squared over 0.95 minus x,
Yeah.
and that's equal to 10 to the minus 4.74.
Yeah.
Sounds to me like all you got is one x in there to solve, right? Just gotta solve for x now. Shall we make this simpler?
Negate the lower.
Let's make an assumption here, right? So if x is very small relative to 0.95, then we can ignore that. Let's see if it works. Somebody who's done the math, what do you get for x? What'd you get?
0.0042.
Yeah.
Right? Okay. Does that, is that really small relative to 0.95?
Yeah.
Yeah, definitely. Okay, cool. We're done. Oh, no, we're not. We gotta do one more thing. Because we haven't actually answered the question yet, which is what's the pH?
Yeah.
We solved for x. Now we gotta solve for pH. What is pH? Not numerically, but what is it?
Negative log of hydrogen presence.
Negative log of H3O plus. Now, and what's the H3O plus?
4.2 times 10 to the
That's that x. Wow. So can you take the negative log of 4.2 times 10 to the minus third?
Sure
I bet you can. I bet y'all have a calculator that'll do that, right?
I did.
If your calculator won't do that, go down to the bookstore and get you a calculator. Okay. So, yeah. So this is my H3O plus. So my pH is
2.4.
2.4. Okay. Yes.
Modifying H3O.
Because that's what pH is. It asks you for the pH. That's why. Remember, this is also that. Okay, so let me ask you this question. What's the PCLO?
It's the same. 14 minus. No, it's the same thing.
It's 2.4.
Yeah, it's the same thing.
Because the H3O and the CLO minus are the same thing.
Yeah.
If I take the negative log of the same thing, I hope I get the same number. Theoretically. Okay. Remember, P just means take the negative log of it, right? Okay, how about this one? What's the POH of this solution?
14 minus 6.
So, what, 11.6?
Yeah.
11.6, yeah.
11.6.
So this would be 2.4, this would be 11.6. You guys see how to do that? It's actually not very hard, is it? You can do this. Okay. Now let's do something similar to what we did in electrochemistry. We were talking electrochem. What if I have two acids? What if I got two acids? So what if I have HClO and HCl? Oh, you know what? We need to do something else first. Let me talk about this first. Strong acids.
Yeah.
Talk to me about strong acids. Tell me about what makes an acid a strong acid.
They break up
completely.
almost completely, nearly completely.
Completely breaks up, right? That's what makes it a strong acid.
Yeah.
Okay, so turns out there aren't very many of those. They're pretty rare.
It's like 7.
Okay? And as a matter of fact, there are 3 binary acids. Binary acids would be H attached to an element. And there's 3 polyatomic acids, which is H attached to a polyatomic ion. Right? Okay. So the 3 binary acids are these 3, HCl, HBr, and HI. And the 3 polyatomics are NO3, SO4, and ClO4. So HNO3, H2SO4, HClO4 is HCl, HBr, and HI. Right? Technically, this and this would also be strong, but not any of it on the earth, so I'm not going to worry about it. Okay. So there's 6 strong acids. Okay. You'll notice that they go up and they kind of curve around O and F, and they're also the ones that have the most oxygens on them. So whatever the most oxygens you can put on N, S, and O, and Cl, and then those binary acids. So HI, HBr, HCl, HClO4, H2SO4, and HNO3. So those are your strong acids. So there's your strong acids. Okay. So anybody else is going to be weak. Okay? All right, so let's talk about HCl and HClO. So if I have HCl, right?
Yeah.
And HClO, I already have that over there, so won't write it again. So those are my 2 reactions that are going on, right? But HCl breaks up, 100% of it breaks up. In other words, this guy is donating tons of these products because it's all breaking up.
Yeah.
Do I share a common ion between these two reactions? Can you see that I do share a common ion?
Yeah.
I have H3O plus.
Yeah.
Le Chalier's principle doesn't care where they come from, it just cares that they're there. So look at what happens to the HClO. I just dumped a huge amount of H3O plus in my solution. Which way is the reaction going to go?
Towards reactants.
Towards reactants, right? And so the stronger acid, by releasing all this extra stuff, forces this reaction backwards. Which means that it keeps the HClO from ever ionizing in the first place. So the H3O plus that I have in that solution all came from this. So when you have different acids, only the strongest one determines the pH. Because the strongest one is going to produce H3O plus that's going to inhibit the other two reactions. Just like, remember when we said if we have two ions in solution, which one's going to oxidize and reduce? Right? Only the stronger one's going to happen. When we have different acids, only the stronger one is going to happen. Does that make sense to everybody? So if you got a mixture of acids, look to find out which one's stronger, and that's the one that's going to determine pH. What if I have acetic acid and hypochlorous acid? Which one is going to, what's going to happen there? Which one's stronger?
The H, not the hypochlorous one.
The acetic.
Well, which is bigger?
That one.
Which one of those is a bigger number?
10 to the negative 4 points.
This one is, right?
Yeah.
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 The stronger one determines the pH. So if you got two compounds, they're two weak acids. What happens if you have a strong and a weak? Which one's going to be stronger? The strong acid has to be, right? Because its Ka is very large. So whatever you come up with, very large wins. Okay? Ooh, what if I have two strong acids?
They're not equally strong, are they?
They're both infinite.
That's the one case where you're just going to add them together.
Okay.
I got very large. I got this one completely breaks up. This one also completely breaks up. They all completely broke up. But in every other case, the stronger one wins. Technically, even with a strong acid, there are stronger strong acids than others, although you can't really tell them apart except by some fancy spectroscopy. But even then, the stronger one goes from infinity to infinity minus 100. Still infinity, right? So it goes from very large to very large minus a little bit. Okay, I don't know what that is. All right. So what's the pH of that solution? 0.95 molar HCl, 0.95 molar HClO. Would it be 2.4?
No.
Which one's stronger?
HCl.
HCl. And what do we know about HCl?
It completely breaks up.
It completely breaks up. So if 0.94, 0.95 molar HCl breaks up, how much H do I get?
0.95.
0.95, because it totally broke up. Well, what's the negative log of 0.95? Right? Good. H plus is that's what pH is, right?
Yeah.
So, like 0.2, I don't know.
0.02.
0.02? Okay, yeah. So this would have a pH of like 0.02. Because see this one, if we set up our ice table here, 0.95, but it's a strong acid. All of it breaks up.
Yeah.
Right? There is none, because it totally broke up. I don't have any X's in this one, which sure makes it a lot easier, doesn't it? I don't have to do anything. So I know what my H3O plus concentration is because it all broke up. And I think we've already confirmed from over here that any contribution, even if this was not suppressed by Le Chatelier's principle, is still irrelevant, right? Because at its worst, even if you had nothing, no interaction between these two, it would only add 4.2 times 10 to the minus third.
Yeah.
So it wouldn't make any difference. All right. Are we good? Got it? Okay. So let's talk for a little bit about bases. What if I got a base? So first off, let's talk about strong bases. What do you think a strong base is going to do?
Fully break up.
Is it going to completely break up? That's what strong means, right? Totally breaks up.
Yeah.
So it's going to completely dissociate. Sorry, numbers have changed. The hydroxides of column 1 and 2 are the strong bases. Okay. Now at this point, let me give you something else. If something is a strong base, that means it completely breaks up. It does not mean miscible. Do you remember what miscible means? We talked about miscible when we were talking about the length of chains of amphoteric compounds, right? Remember we talked about those?
Dissolved in water.
Miscible means infinitely soluble. Okay? So the 2A hydroxides especially, all of it that dissolves completely breaks up. It does not mean that all of it's going to dissolve. It means that to the extent it dissolves, it totally breaks up. That makes sense?
Mm.
Now that's actually used a lot in medicine. For example, milk of magnesia is used for heartburn. It contains magnesium hydroxide, which is a strong base, but not very soluble. If you've ever seen milk of magnesia, it's a white suspension because most of the magnesium hydroxide does not go into solution. Okay? Which means you can drink it without killing yourself.
Yeah.
Because you can imagine, milk of magnesia, Drano.
Oh, jeez.
I don't think I want to drink the Drano because it's very soluble in water and it's going to burn all the tissues all the way down to my stomach. Would it take care of the heartburn? Sure. On its way through the rest of you as it ate its way all the way out and came out your toes.
That's gross.
Milk of magnesia, on the other hand, not very soluble. And so even though it all breaks up, it still doesn't it doesn't raise the pH that much. And so you don't like burn all the way down until it hits the acid in your stomach, at which point the H3O plus reacts with the OH, and now it dissolves. So it only dissolves in your stomach. Once Le Chatelier's principle gets involved, eating all that acid in your stomach, instead of eating all the tissue on the way down to the stomach like Drano would do. You see a difference there? So there's a lot of opportunities there to utilize that. I think Rolaids are the same. Rolaids are the same, except it's aluminum hydroxide. Okay, so those are our strong bases. So let's take a different base. Let's see, what is the pH of a 0.15 molar NH3 solution? pKb is 4.74. It's actually one of the real mysteries of life that I don't know anybody's been able to figure out, that vinegar and ammonia have the same K, except one's a Ka and one's a Kb, but they have the same number. Two very common compounds with the same. Someday one of you will figure that out and probably win the Nobel Prize for it, so go figure it out. Win the Nobel. So what's the first thing I'm going to do? Write the equation, like we always do, right? First thing we're going to do is write the equation. So what's ammonia going to react with?
Water.
Water, right. So have ammonia react with water.
You get ammonium hydroxide.
Is ammonia a strong base, weak base?
Weak base.
Weak base, how do I know it's a weak base?
No hydroxide.
It's not in column 1 or 2. And also, I gave you a pKa or pKb,
That too.
Yeah.
right? Because if it's strong, it's not going to have one of those. It's just going to be really big. So NH3 is going to react with water. And what am I going to get? This is a base, right?
Yeah.
What does a base do?
Mix hydroxides.
No. That's the
Accepts-
Arrhenius definition. In Bronsted-Lowry, what does a base do?
Except hydrogen.
Accepts a hydrogen, right? Okay, where's it going to get the hydrogen from?
The water.
Water. And so after it accepts a hydrogen, it's now NH4. After this loses a hydrogen, it's OH minus. Okay? So in the Arrhenius definition, there's no such compound, there's no such base as ammonia. They would tell you, the Arrhenius people for 100 years would say, the base is ammonium hydroxide. The NH4OH is the actual base. That's what they would say. And as a matter of fact, you can still see glass edge bottles, they'll say ammonium hydroxide on them. Matter of fact, we even have some bottles in our lab right now that say ammonium hydroxide. All right, so, guess we want to set up an ice table, huh?
Sure.
what is what is what is 10 to the minus? See, there's your problem. You're hitting us. Just try.
Sit down.
I don't know exactly what it is, but it's, are you getting it even? Okay, so it's one.
So minus 6. Well, the pH
Now
is
multiply that by
H plus.
And that makes it.
She took the pH first. Since we went through 14 things.
So I'm seeing KB is 10 to the minus 4.74, which is 1.82 times 10 to the minus fifth.
Yep.
And that's going to be equal to x squared over 0.15 minus x.
Yeah.
Right? Is that what you got?
Yeah.
And so we're going to drop that. So if x is really small relative to 0.15, and then we get x, which is, I don't remember what that is. So what'd you get for x? What? 1.7 times 10 to the
Negative 3.
negative third? 1.7 times 10 to the minus third. Okay?
Yeah.
Is that less than 10% of this?
Yeah.
Yeah, because this is smaller than 0.015, right? Okay, so we're fine. Okay, so the assumption's good. And what does this stand for? What is x? What is x?
OH.
It's my OH
And NH.
and my NH formulas,
But we don't care.
which in this case I don't need, but it's there, right? Okay. So we could probably take the negative log of this number,
Yeah.
and what do we get?
2.78.
2.78? Okay. And what is that?
POH.
POH. So the POH is 2.78, but question is, what's the pH?
14 minus.
So the pH is 11.22.
Yeah.
Does that fit with what we know about ammonia?
Yeah.
We know ammonia is a base. So what kind of pH does it have to have?
Over
It's got to be over 7. 11.2 is definitely over 7, right? So we're okay.
Yeah.
So it worked. Do you see how it doesn't make any difference whether we're talking an acid or base? The math is the same, right? Just remember, what does X stand for? You got to look at the original equation. If I did a base, I solve for X and I go, oh, but X is OHs. I'm always going to be asking you for the pH of something because that's just the way people talk. You know, you don't go, oh, well, the POH of this base is 3. People wouldn't know what you were saying. They go, oh, the pH of this base is 11. That's what they're going to actually tell you, right? Because we have pH paper, we don't have POH paper. Technically, we could. We could have POH paper. It's just people don't want it, so we don't have it. Right? We could do it. All right. So that's how you do a base. Work just like an acid. Just remember, when you see the K, look at that subscript. Is it a Ka or is it a Kb? Right? All right. Okay. Well, the next thing to talk about is what do you do if it has multiple H's on it? What do you do if it's like this? Boric acid. Now here's where the way acids work helps you out. If you remember, when you do a reaction, it's products minus reactants raise the power of the coefficients, right?
Yeah.
Products over reactants raise the power of the coefficients. But you can imagine if we did this, I'm going to be raising this to the third power, and that's going to be the second. This is going to be some sort of power, fourth power polynomial type thing.
Yay.
Ew, that doesn't sound fun.
No, it's
But it turns out this is not what happens. All three of those hydrogens may come off, but they come off one at a time. And when the first one comes off, you remember when we were doing ionization energies and we said, okay, here's the ionization energy, first ionization energy, now we pull the electron off, all the electrons go whoomp and scrump down in, and now it's harder to pull the second one off. And then whoomp, they scrump in, and it's harder to pull the third one off. Well, same thing here. You pull that first one off, everything crumps, and it's hard to pull that second one off, i.e., the equilibrium changes. And so every hydrogen has its own equilibrium constant. So we never have to worry about those powers, because let's do it for item 1, for the first hydrogen. And it solves x squared over whatever minus x. And then, okay, now let's solve for the second one. And it's also x squared over whatever minus x. Now let's solve for the third one. Okay, well that's how we're going to do it. So when we do these, you pull them off. You do it like that. You pull off one hydrogen. And so this right here would be Ka1. And then this, probably I'll put it over here. Then this is Ka2. See how it works?
Yeah.
And then you can hypothesize the third one. I mean, it's gonna be the same. Okay. So, there we go. So you should all be able to solve that first one without any difficulty,
Yeah.
hopefully. So take that first hydrogen off to be able to do that, right? So 10 to the minus 10.33, that's pKa, that's Ka, is equal to x squared over 0.2 minus x, but let's ignore it. Let's assume that the x is going to drop.
H2S small.
Okay? So when you solve for x, we get something.
3.06 times 10 to the negative 6.
Did y'all get that?
That's right.
What's that equal to?
H.
That's equal to the H3O plus and the H2BO3 minus. Right? Now we got to come over here and do the second one. But look, 3.06 times 10 to the minus 6 is how much of that we have. That actually tells us how much goes on. But we don't start with 0 on the H3O plus. We do start with 0 here because we haven't seen it yet.
Just gonna add them together, right?
But other than that, it works the same as the other one.
It's negligible effect as you go on.
Yeah.
Why is the H2O3 0?
Why is the what 0? The HBO3?
Yeah.
Because I've never seen it before. I don't have any HBO3 from that prior reaction.
Super diminishing
I
returns.
could only take the ones that I actually have some of that I haven't. So 10 to the minus 12.60 equals 3.06 times 10 to the minus 6 plus x times x over 3.06 times 10 to the minus 6 minus x. Okay? And what's our assumption we're going to make?
X.
If x is really small relative to 3.06 times 10 to the minus 6,
It is P.
then what can I do?
Go
I
back.
can drop this x, right?
Yeah.
Yeah.
Oh, well, hold it. If it's irrelevant to subtract it, isn't it equally irrelevant to add it?
Yeah.
Yeah.
If I say, how much do you weigh? And then I take off a dander flake, or, ooh, heaven forbid, I put an extra dander flake on you,
Ew.
I still haven't changed your weight, right?
Seasoning.
Didn't matter whether I added or subtracted it, it was irrelevant. So in that case, if this is irrelevant, then that's irrelevant too.
And those two can't.
Hold it, but if that's irrelevant, is that irrelevant?
Yeah.
No, because I multiply it. You can't make that, you can only do that with addition and subtraction.
Yeah.
You can't do that with multiplication. But hold it, if I get rid of those,
The constants cancel.
the constants cancel. Oh, wow, that just became super simple. Everything canceled except x. So what is 10 to the minus 12.6? I don't know what that number is.
2.5 times 10 to the 13. 2.5, not 2.05.
Oh,
5.1 if you want another sig fig.
is that small relative to 3.06 times 10 to the minus 6?
Yeah.
Yeah. Cool, so the assumption was valid. It all drops.
But if it's small relative to 3.06, does that mean we can ignore it?
Well, now hold it.
Overall.
HBO3 minus 2 plus H2O. I still got one more, right? Ka3. H3O plus BO3 minus 3. So what's my initial? What's my initial HBO3? It's gonna be this, right?
It's just more. We're not multiplying.
What's my initial H3O plus?
3.06 times 10 to the negative 6.
3.06 times 10 to the minus 6 plus 2.51 times 10 to the minus 13th, which we've already decided is irrelevant, but whatever, I'll put it in there because I know the number. Okay, although I'm sure my calculator doesn't have enough zeros to actually figure out what that number is. And this is 0.
Yeah. This is getting silly.
All for K3. So 10 to the minus 13.14 equals 3.06 times 10 to the minus 6. I'm just going to go ahead and drop that. Plus x times x over 2.51 times 10 to the minus 13 minus x.
Yeah. Okay.
So if x is small relative to 2.51 times 10 to the minus 13, then that drops.
Yeah. And
But if it's small enough it's irrelevant to that, it's really irrelevant to this one,
yeah.
right? If a piece of dandruff is irrelevant to you, it is really irrelevant to Jupiter. Okay? Yeah. So that's not going to work.
Yeah.
So both of those will drop. Cool. So what's x? Yeah.
If you had kept the 2.51 to 10 to negative 13 on the top, would it cancel out with the bottom? Or no? With A3 plus?
Well, if x is irrelevant, if we already know this is irrelevant to this, and this is also going to be irrelevant to that, so it's not going to matter. They'll both drop, whether I put it in. So I don't know. Somebody give me what x is.
I did not get that.
Real fast. What'd you get?
1.2 times 10 to the negative
7.2 times 10 to the minus 14.
Divided by 3.06.
I would think it's going to be like 10 to the minus 20th.
Yeah, 5.95 times 10 to the negative 21st is what I got. Yeah.
Okay, because that's, just rough guessing, that's 10 to the minus 7, right? Or 10 to a positive 7. So when I multiply over here, or whatever, it's going to add 7 to that number. So it's going to be in the 20-21 range. Okay, now take a look. What's the pH? The pH is an H3O plus concentration, which is this plus this plus this. This plus an irrelevancy plus an irrelevancy.
Yeah, so it's just the initial.
And that is universally true. There's the punchline, guys. If you have a polyatomic acid, Ka1 determines pH.
Yeah.
The other two are too small. They don't count. Okay? So anytime you have a polyprotic acid, Ka1 determines pH. Okay? Cool. See you Friday. Yep.
That's much better.
For the third one, I was expecting to get that.
Which part?
Overall sensibilities.
That should be adopted everywhere.
You did not get that?